The most popular joining approaches used to join two or more bodies together also rely on elastic deformations to achieve their objective. Most consumer products consist of multiple manufactured parts that need to be joined together during assembly. The joining approach chosen to attach these parts often determines the final product's quality and performance, because most failures occur at the interface of the product's joined parts. Although some joining approaches don't rely on elastic deformations, such as welding or gluing, the vast majority of such approaches do rely on elastic deformations to fix their parts together. Screws and bolts are common but unlikely examples of joining elements that rely on compliance to function. At first glance, bolted joints may seem like a collection of rigid parts, but the bolt itself doesn't successfully join the parts together until its shank begins to stretch as the joint's nut is tightened. It is only at that point that the bolt begins to permanently join its parts together through compression, such that the forces required to shear them apart are far greater than those expected to load the joint during its lifetime. Thus, it's the elastic nature of the part's deformations that actually joins them together. Some latches also appear to be made of rigid pieces, but they too use compliance to join their parts together. Only when this joint's switch is pushed down so that its compliance strap is elastically stretched around its drum does the joint properly function. Press-fit joints also rely on elastic deformation to join their parts together. Dowel pin joints are a good example. The outer diameters of dowel pins are intentionally made larger than the holes into which they are hammered, so that the material surrounding the pins compresses them with a significant enough elastic force to hold them firmly in place. Other press-fit examples include bottle corks, Legos, and other toy building blocks, the plugs on the inlets of inflatable beach balls, the fasteners on the back of some baseball caps, removable erasers, poster tube caps, and the lids of many containers. Another joining mechanism that uses elastic deformations to function is a compliant snap fit. Unlike the previous joining approaches discussed, the flexible elements that constitute snap fits elastically deform as they are being joined together, but once the parts are in place, the elements snap back to their original configuration where they become anchored in place, like this common snap buckle. Many laptop cases use internal springs within latches that achieve snap fit behavior to help their cases remain shut. Other compliant snap fit examples include Ethernet cable connectors, phone cases, plastic eggs, binder rings, clips for vacuum cords or sun visors, pen caps, some CD cases, clothes buttons and hangers that deform to clamp clothing in place, fasteners like the one used to join the ends of this goggle's straps together or to clip children into car seats, and latches like the one used for this cake lid, this coin pouch, this clock's battery panel, and this styrofoam food container. In fact, many container lids use snap fits to seal themselves shut once they have been closed. This soda lid not only snaps onto its cup, but it also possesses compliant flaps for pinching straws in place and preventing backsplash. Ziploc seals also use snap fit principles to join two sides of a bag together. A parallel track of opposing J-shaped grooves or hooks on one side of the bag snap onto another arrowhead-like stem on the other side of the bag when pressed together, thus causing an airtight seal so food within the bag can remain fresh. Zip ties are another snap fit inspired device, but the neat thing about zip ties is that there are many different positions into which the teeth on its compliant band can snap as they are pulled past a deforming beam within the zip tie's ratchet head. Since the compliant beam in the ratchet head is only allowed to deform in one direction, users can easily adjust how tightly objects are bound together. But once snapped in place, the zip tie's compliant band can't be pulled out the other direction. Nature has also leveraged elastic deformations to devise a variety of simple but ingenious joining approaches that have inspired numerous products. The concept for touch fasteners was, for instance, inspired by nature. Swiss engineer George de Mestral invented the first man-made touch fastener in 1941 after he went on a walk in the woods and noticed how easily burdock seeds would cling to his coat. Upon closer inspection of these and other hooked seeds that passively attach themselves to almost anything that brushes against them, he was inspired with the idea for Velcro. Velcro consists of two mating sides. One side consists of looped fibers, and the other side consists of tiny elastic hooks that deform around and tangle themselves with the loops of the other side when they are pressed together. Since the loops elastically deform when the sides of the resulting joint are forced apart, Velcro can be used multiple times until the sides become overly clogged with dirt and debris. Velcro is often used as an easy alternative for rapidly fastening shoes, gloves, and other wearable items such as these elbow pads. Suction cups leverage another nature-inspired joining approach that also relies on elastic deformation to function. Similar to the suckers on an octopus or a squid, suction cups push the air out from underneath them as they are elastically deformed onto the part to which they are intended to be joined. If a load tries to pull the suction cup off of the part's surface, atmospheric pressure pushes back on the cup against the vacuum created within the sealed chamber below it, and thus the cup remains firmly attached to the surface. Suction cups are most often used when a part is intended to be attached multiple times to an unanticipated but smooth surface without damaging the surface or leaving behind a sticky residue from a liquid adhesive. Examples include bathroom shower mirrors, the bases of some toothbrush handles, or windshield phone holders. Note that this phone holder is also spring-loaded to accommodate differently sized phones. Geckos have evolved an ingenious approach for attaching to almost any natural or unnatural surface using elastic deformation in conjunction with other surprising physical phenomena. The approach enables their feet to passively attach to vertical walls with adhesive forces that can withstand 40 times their weight in the downward shearing direction. Even more amazing is that their joining approach allows their feet to immediately disengage from and then reattach to walls fast enough to permit them to run away from oncoming predators and seemingly defy gravity by hanging upside down. The joining approach that geckos use remained a mystery until the year 2000, when Kellar Autumn from Lewis and Clark College and Robert Full from Berkeley examined the feet of geckos in a scanning electron microscope. They discovered that the underside of a gecko's foot possesses ridges on which uniform collections of tiny hair-like structures are organized. The tips of each of those hair-like structures branch into many other even smaller nano-sized structures. When the gecko's foot shears down along a vertical wall, the entire forest of branching hair-like structures on the underside of its foot elastically deform such that they lay down on the wall's surface. When configured in this way, an immense amount of direct surface area contact exists between the hair-like structures and the wall. With such immense surface area contact, the usually weak van der Waals forces of attraction between the foot and the wall produce intermolecular adhesive forces which collectively resist remarkably large loads that far exceed the gecko's weight, but only in the shearing direction. When the gecko directly lifts its toes in the direction perpendicular to the wall's surface, all the elastic hair-like structures spring back to their normal shape, and the attractive forces to the wall immediately disappear so the gecko's foot can quickly reposition and attach elsewhere. Thus, by leveraging the compliance of millions of elastic nanofeatures, geckos achieve both dry and directional adhesion. Now, there are many more compliant examples, and even entire categories of compliant examples that we could have discussed, such as art or photography. But hopefully by now, you're starting to realize the extent to which compliant devices have completely infiltrated your daily life. Despite how ubiquitous compliant products are, though, examples in nature suggest that the advantages of compliant deformations are still majorly underutilized by society. Instead of using them for toys and toilet plungers, we could be using the advantages of compliant deformations to create technologies that push the limits of what's physically possible and unlock the door to transform our current perception of science fiction into a compliance-enabled reality. So stick with this course, and I hope you can learn what you need to play a role in bringing about this potential reality. Thanks for watching. I hope you enjoyed part 2 of my Compliant Mechanism Design course. Be sure to watch part 3 to learn about the fundamental principles of deformation in the context of even more compliant examples. But before you watch part 3, my first assignment to you is to try and think of other common compliant examples that I failed to mention in this video, but that use elastic deformation to achieve their function. Please post your examples in the comments section below so that everyone can benefit from what you find. Also, be sure to check out my website to access free online resources that supplement this course with optional reading materials, assignments, and practice problems. The link to the website is in the description below. Good luck with your assignment, and thanks for contributing to the library of compliant examples.